Welcome to section 2.4. We've been talking a lot about functions in chapter 2. Now we're going to be looking at what types of operations can be performed on functions. Also continue looking at domain and what happens when we use these different type of operations. We're going to start with the definition. We're going to start with a definition. We have for two functions f and g, the sum, difference, product, and quotient functions f plus g, f minus g, f times g, and f divided by g respectively are defined as follows. F plus g of x is equal to f of x plus g of x. We have that f minus g of x equals f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x is the same as f of x divided by g of x, provided g of x does not equal 0. We know that our denominator cannot equal 0 if we're working with a fraction. Alright, so with these definitions in mind, let's take a look at some examples. So in example 1, we have let f of x equal 3 times the square root of x minus 2 and g of x equal x squared plus 5. Find and simplify each expression. In part A, we've got f plus g of 4. Okay, so if you look back up at your definition for addition, f plus g of x equals f of x plus g of x. So that tells us that we can write this as, what is our x here? The number here we see in parentheses, that's our x. And the f and the g are our functions. So this can be written as f of x, f of 4. Our x is 4. f of 4 plus g of 4. Let's find f of 4. This is our function f. f of 4 is telling me to put 4 in for x. So f of 4 I could put right here. If I put in 4 for x, take the square root, so I've got 3 square root 4 minus 2. So that's square root of 4 gives me 2. 3 times 2, that gives me 6 minus 2. So f of 4 is equal to 4. So that can go right here. f of 4 is the same as 4. Let's find g of 4. So go to my g function, put 4 in for x. That gives me 4 squared plus 5. So it gives me 16 plus 5, or 21. So we're going to add 21. Alright, so f of 4 gave us 4, g of 4 gave us 21. Add these together. Our answer is going to be 25. Part B, we need to find f minus g of x. The rule for subtracting functions is very much like the rule for adding functions. We need to do f of x minus g of x. This one's a little different than the previous one. In the previous one we had a specific value to substitute in for x. This time we're just working with x in general. So f of x we see is defined as 3 times the square root of x minus 2, so we can make that substitution. Be careful that your square root symbol does not extend past your x. So 3 square root x, and then the minus 2 is on the outside. Minus, and then g of x. g of x is x squared plus 5. Notice you're subtracting a binomial, so you need to have it in parentheses. So this is our f of x here, and then we're subtracting our x squared plus 5, our g of x. And we can distribute. So we have 3 square root x minus 2 minus x squared minus 5. And we can also combine the constants because those are like terms. So we have 3 square root x, negative 2 minus 5 gives me minus 7. Minus x squared, and that is my answer. 3 square root x minus 7 minus x squared. let's go on to example C. As I'm going through these, I'm not going to be telling you to pause as frequently as I have in previous videos. Use your own judgment on that. If you need to hear me repeat something, just stop it and go back and listen to it again. But we're going to keep right on going here for the most part. So let's go on to part C. We're still using the same definition. Alright, so our definition, this is our, I'm going to get my paper straight. There we go. So we're still using these same functions, f and g, for example 1. So we still have f of x equals 3 times the square root of x minus 2. G of x equals x squared plus 5. We still want to find and simplify each expression. Part C, we want to do f times g of 0. Alright, again, if you look back at your definition, you'll see that doing f times g of a value is the same as doing f of that value times g of that value. So we want to do, I'll go back to my colors again. We want to do f of 0 times g of 0. Alright, what's f of 0? Go back to the f function. I need to put 0 in for x. So that's going to give me 3 times the square root of 0 minus 2. Alright, square root of 0, hopefully you know that is 0. Multiply by 3, you still have 0, and then subtract 2. So f of 0 is negative 2. Alright, g of 0. Here's my g function. Put 0 in for x. I've got 0 squared plus 5, which gives me 5. So when you're going to multiply 5 to the negative 2. So negative 2 times 5, and I apologize, I accidentally wrote a negative. So we found f of 0 to be negative 2, g of 0 was 5. We're going to multiply those together, and our answer is negative 10. And then part D. So that's how we got part C. Alright, let's move on to part D. Still using the same original functions. We've got f of x equals 3 times the square root of x minus 2. G of x equals x squared plus 5. And we need to find f over g of 9. Alright, so again, my rule tells me to break this apart as f of 9 divided by g of 9. And I apologize, you probably didn't see what I just wrote. F of 9 divided by g of 9. According to our function, we need to find f of 9, so put 9 in here for my x. And that's going to give me 3 times the square root of 9 minus 2 on the outside. There we go. 3 square root 9 minus 2. And then when we do g of 9, we saw, remember g, our g function was this x squared plus 5. So we need to put in 9 for this x. So our denominator needs to be 9 squared plus 5. And then we'll simplify this. So square root of 9 is 3. 3 times 3 is 9. Subtract 2, that gives me 7. In the denominator, 9 squared is 81. Add 5, we get 86. So our answer is the fraction 7 over 86. That's a 7 there. Okay. Example 2. We are asked to let f equal the function of, or the list of ordered pairs with order pair 1, 3, 2, 8, 3, 6, 5, 9. And then function g will be the set of ordered pairs 1, 6, 2, 11, 3, 0, 4, 1. We are asked to find f plus g, f times g, and f divided by g, and to state the domain of each. Okay, so in this problem, it's actually easier to start by finding the domain. How do we find the domain of these types of operations? Well, let's just look at f plus g for a moment. F plus g is asking me to find values that are in both sets and then add them together. And we need to start with x values for our domain. So if we start with f plus g, and I'm going to make a column here to separate my work. So for f plus g, let's look at the domain. The domain will be values of x that we see appearing in both of our sets. So what x values do you see that occur in both set f and in set g? This is the same thing as finding the intersection of the two sets, or for the x values, excuse me. So what x values do we see occurring in both sets? Well, we have a 1 that appears in both of them. They both have x values of 2. They both have x values of 3. Okay? Those are the only x values that both sets share. So that's everything that goes into the domain. Once we have the domain, we can go ahead and find the addition operation for these two functions. So to find f plus g, we need to start with our first element in our domain. Let's do f of 1 plus g of 1. So if we find f of 1, what is f of 1? Find function f, put 1 in for x. What do you get back for your y? If when x is 1, y is 3. Alright, so we get 3 here. Excuse me, I'm sorry, f of 1 is 3. What about g of 1? So remember, we're doing f plus g. We have found f of our first element. Now we need to find g of our first element. So go to the g function. When x is 1, what is y? Well, if we go to the g function, if x equals 1, y equals 6. So g of 1 is 6. We add these values together, we get 9. Okay, so that tells us that for the f plus g function, when x equals 1, y equals 9. So that gives us our first ordered pair, 1, 9, that goes into the f plus g function. Okay, now we need to do the same thing, but we need to do it for x equal to 2. So I'm going to give you a moment to think about that, and I'm going to have you pause here. Go ahead and pause, and you find f plus g of 2. Okay, so let's see what happens. What is f of 2? F of 2 should have given you 8. Let me put it there, excuse me. And then we want to do g of 2. G of 2 should have given you 11. And then you add these together and you should have gotten 19. So this ordered pair is giving you 2 for x and 19 for y. So that's the second ordered pair that we can put into the function f plus g. Alright, is there anything else in our domain that we need to calculate? Yes, we found the y value when x was 1, and we found it when x was 2. Now we need to do the same thing when x equals 3. So now we want to find f plus g of 3. Alright, so we're going to do f of 3. What is f of 3? go ahead and find f of 3, find g of 3, add them together. So f of 3, if you go to the f function, when x equals 3, y equals 6. G of 3, go to the g function, when x equals 3, y equals 0. So we're going to do 6 plus 0. So f plus g of 3 is giving us 6, and that is the ordered pair. Our x was 3, our y is 6. So we have found that f plus g is equal to the set of ordered pairs (1, 9), (2, 19), and 3, 6. So we have answered the question. They had asked us to find the domain 1, 2, 3. F plus G was ordered pairs 1, 9, 2, 19, 3, 6. I said we have answered the question. We've not finished, however. They also want us to find F times G and F divided by G. So we still have some more pieces of this to go, but we've answered the first part. We have found F plus G, and we found its domain. All right, so let's move on and look at, I'm going to, you've got space in your notes that you should be able to do the remaining 2 pieces on this page. However, I need to be able to keep my function up there so I can easily see it, so I'm going to move mine onto a separate piece of paper. Let's find f times g. Again, our domain, we start with, we can only use these values for x. So to find f times g of 1, we know that f times g of 1 is equal to f of 1 times g of 1. So what is f of 1? If x equals 1, go to your f function. We already found this to be 3. G of 1, we already found that to be 6. So f times g of 1 equals 18. And this gives us the ordered pair 1, 18. Alright, let's do the same thing for x equal 2. We're going to find f times g of 2. So we want f of 2 times g of 2. F of 2, go to your f function, let x equal 2, we already found that to be 8. G of 2, we already found to be 11. Multiply those together, and we get 88. And we have the ordered pair 2, 88. And then if x equals 3, put it over here. If x equals 3, we want f times g of 3. We know that's f of 3 times g of 3. F of 3, we found already. That was 6. G of 3, we already found. That was 0. Multiply those together, you get 0. This gives us the ordered pair 3, 0. So we have found f times g to equal the set of ordered pairs 118, 288, and 30. And now we're left to find f divided by g. And again, I'm going to have to go to a separate sheet of paper. So rewind this if you need to, watch it again. And I'm going to have to go to another page to do my calculations for the last part. For f divided by g, go back to your domain. If x equals 1, find the f value, find the g value, and then divide. So we know f over g is equal to, f over g of x is, we'll let x equal 1. So f over g of 1 is f of 1 over g of 1. What is f of 1? Again, these are the same values that we've already calculated. If go to your f function, if x equals 1, y equals 3. To get g of 1, go to your g function. If x equals 1, y equals 6. And that 3 over 6 would reduce to 1/2. So that gives me the ordered pair 1, 1/2. To find f over g of 2, we want f of 2 over g of 2. F of 2 we found to be 8. G of 2 we found to be 11. So that gives us 8 over 11. Our ordered pair here is going to be 2, 8 over 11. F over g of 3 is f of 3 over g of 3. F of 3 we found to be 6. G of 3 is 0. Alright, but we have a problem here. We've got 6 over 0. We cannot divide by 0, so this is not giving us a legitimate value back. That means that the domain of f over g is not the same as the domain of the previous operations. For this one, for f over g of x, our domain is just going to be the 1 and the 2, because the 3 is not giving us a legitimate value for y. So for f over g, my domain is just 1, 2. So that would give me just these two ordered pairs. So we have f over g equals the list of ordered pairs 1, 1/2, and 2, 8 elevenths. And that's f of g. Moving on to example 3. In example 3, we're given f of x equals the square root of x, g of x is equal to 3x plus 1, h of x equals x minus 1. Find each function and state its domain. So to do f plus g, we use our same definition we've been using before. We know that we want to find the f function, find the g function, add them together. We're given the f function, that's the square root of x. So this is going to give us the square root of x plus our g function is the 3x plus 1. And there are no terms that we can combine here, so this is our answer for f plus g. They also want us to give the domain. Alright, to determine the domain, what do we have going on here? What kind of restrictions do we have on our x's? If you're working with the square root of x, then you have to be careful that you don't ever have the inside of this becoming a negative value. So your domain here needs to be, the inside must be greater than or equal to 0. So you can say x is greater than or equal to 0. The interval notation for this would be square bracket 0, infinity. So this is our domain, and this is our f plus g function. In part B, we need to find g over f. So this time, we need to do the 3x plus 1 divided by the original f function, which was the square root of x. This time for our domain, we've got a similar issue as over here, but we also have the square root in the denominator of a fraction. So not only does x have to always be positive, it also can never be 0. So here, your domain, you can think of this as the square root of x has to be strictly greater than 0. It cannot ever equal 0. So your interval notation would be parentheses 0 comma infinity for the domain. So there's your domain, parentheses 0 to infinity, and the actual function, the g over f function, is 3x plus 1 over square root x. Alright, I'm going to have to pause it so I can get part C and D on here. Part C, we're asked to find g times h. So we know that we need to multiply the 3x plus 1 from g times the x minus 1 from h. So we've got 3x plus 1 times x minus 1. We can go ahead and FOIL this out. That gives us 3x squared minus 3x plus 1x, so minus 2x minus 1. My domain, do I have any restrictions on x this time? I don't see any square roots, and I don't see any fractions with a denominator with it including an x. So I don't have any restrictions on x. I can put anything into this for my x and always get a legitimate value back for my y. So my domain here is negative infinity, positive infinity. For part D, I need to find g minus h. So I need to take the 3x plus 1 from g, and subtract the x minus 1 from h. I can distribute that, 3x plus 1. Make sure you remember to use parentheses when you subtract your binomial. Minus x plus 1, so it gives me 2x plus 2. And my domain this time, what do you think my domain is? We're looking at this piece here. Are there any restrictions on x? No square roots, there's no fractions with denominators of x. So my domain is negative infinity, positive infinity. And that's it for part D. Alright, now we've got a definition to discuss for composition functions. Alright, this is a pretty wordy definition. So we'll go through it. If f and g are two functions, the composition of f and g, written f composite g, is defined by the equation f composite g equals f of g of x. In other words, you're putting the g function inside your f function, provided that g of x is in the domain of f. The composition of g and f, written g composite f, is defined by g composite f of x equal g of f of x, provided that f of x is in the domain of g. Okay, so what this is really saying is that when you see this notation f composite g, this means that you're going to put the g function inside the f function. When you see the notation g composite f, this is asking you to put the f function inside the g function. Cool, so let's look at some examples of how this is going to work. Example 4. G is the function with ordered pairs 1, 4, 2, 5, 3, 6. F is the function with ordered pairs 3, 8, 4, 9, 5, 10. We're asked to find f composite g. So again, this is telling us to take the g function and substitute it into the f function whenever possible. It may not always be possible for these examples, but looking at the g function, this is going to be our starting point, is the one on the right. Go to the g function here. If x equals 1, okay, well, if x equals 1 in the g function, y is 4. Alright, then that result needs to go into the f function. So do we have a 4 here? Yes, we do. So we can calculate this one. So we'll go ahead and say what our domain is first. Okay, so again, go into the g function, letting x equal 1, we get 4, and then go to the f function and see if you have an x value of 4, and you do. So that one can be, the composition function can be calculated when x equals 4, so 4 can go into the domain. I'm sorry, 1 can go into the domain. excuse me, 1 can go into the domain because, again, this x value of 4, we started on the right side with the function g. We go to the g function and we see that if x equals 1, y equals 4, and then we check to see if we can find f of 4. So go to the f function, and we do have an x value of 4, so we can calculate f composite g of 1. And then go back to the g function again, because it's the one on the right. Remember, the definition is telling us to substitute the g function into the f function. So going back to the original g function, the next x value that we come to is 2. Can we calculate f composite g of 2? Well, we'll start by finding g of 2, which is 5. Can we put 5 into the f function? Well, yes, there's an x value of 5, so we can calculate f composite g of 2. What's the next x value in our g function? It's the 3. Can we calculate f composite g of 3? Well, we start by finding g of 3, which is 6. Can we put 6 into our f function? Can we calculate f of 6? Well, there's no 6 listed as an x value, so 3 does not go into the domain of f composite g, only 1 and 2. Now that we have our domain, our x values for f composite g, we'll go ahead and calculate this. And this is really not that hard once you know how to proceed. So if x equals 1, we start by finding g of 1. What is g of 1? Come up here, g of 1 is 4. Now I need to put 4 into my f function. So I calculate f of 4. Go to the f function, find the 4. My y value would be 9. So that tells me that f composite g of 1 is equal to this 9 that I got here in my last step. What if x equals 2? If x equals 2, I start on the right. I find g of 2. Go to the g function. G of 2 is 5. Now take this 5 and put it into the f function. So f of 5. What is f of 5? 10. So that tells me that f composite g of my original x value 2 was 10. So that means f composite g, if I list these as ordered pairs, is the set of ordered pairs 1, 9, 2, 10. Alright, again, watch that again if you need to see it again. Long story short, composition function, you're taking the function on the right, substituting it into the function on the left. In example 5, we're doing a very similar procedure, but now we're working with equations instead of lists of ordered pairs. Alright, so in example 5, we have f of x equals the square root of x, g of x equals 2x minus 1, h of x equals x squared. Find the value of each expression. F composite g of 5. We know we start with the function on the right when we're working with composite. And I'll go ahead and say, be very careful that you don't confuse your composite symbols with multiplication. The composite symbols will always be a little open circle. You can probably see it a little bit better over here, but in your notes, again, you can see that your composite function is always an open circle. Multiplication was just a dot. We're going to start by finding g of 5. So you need to go to your g function, put 5 in for x, and that gives you 10 minus 1, so 9. Now this number needs to go into your f function, so you want to find f of 9. Here's your f function. That would give you square root 9, which is 3. So that tells me that f composite g of 5 equals 3. part B, we need to find G composite F of 5. Now, do we expect this to give us the same answer as the previous one? No. F composite G is not necessarily the same thing as G composite F. So we'll start by F of 5. I'm going to let you do this part. I'm going to ask you to pause now. And I'm going to give you a few seconds. I want you to go ahead and calculate G composite 5. So for F of 5, that gives you the square root of 5. And now you need to calculate G of square root 5. So go to the G function. You're going to have 2 times the square root of 5, and then minus 1 after the square root. And this is your answer. Alright, in part C, I'm going to see if I can, I'm going to pause for a second and get this organized. Part C, we're going to find H composite G composite F of 9. So again, we're going to always start with composite functions. We're always going to begin on the right and gradually move to the left. So we start by finding F of 9. Alright, F of 9 we've already found to be 3. Now we want to find G of 3. So put that in here. 2 times 3 minus 1 gives us 5. And now 5 needs to go into the H function. So find H of 5. That's going to be 5 squared, or 25. So my answer is, so H composite G composite F of 9 is equal to 25. Example 6. Let f of x equal square root x, g of x equal 2x minus 1, and h of x equal x squared. Find each composition function and state its domain. So f composite g, still substituting the right function into the left function. So we need to put this 2x minus 1 that we see from g inside our f function in place of the x. So that becomes the square root, and then you substitute the 2x minus 1 inside for the original x. How do we get the domain for this? We go look at the inside of that square root function, 2x minus 1. If it's inside a square root, it must always be positive, so it's got to be greater than or equal to 0. Solve that for x. We get x is greater than or equal to 1/2. So our domain would be the interval square bracket 1/2 comma positive infinity. So that's my domain, and this is my actual function. In part B, I'm finding G composite F. This time I need to substitute my F function inside my G function. So I'm going to put my square root of x inside here in place of my x. So I'll get 2 times the square root of x and then minus 1 outside the square root. For my domain, I know that I cannot have a negative inside that square root, so I can calculate. I don't even really have to make a calculation. I know that x, the inside, must be greater than or equal to 0. So my domain would be the interval square bracket 0 comma infinity. Alright, and then for part C, we're going to calculate F composite H. This one I made a little correction in your notes. Not really a correction, but a clarification. And your original was a little, it wasn't clear, but that's an open circle for composite. So for F composite H, you're going to put H inside your F function. So you're going to put the x squared inside here. That's going to give you the square root of x squared. And we know that if we do the square root of x squared, they always cancel each other out, which just gives me an x. For my domain this time, my result was just regular x, so that can be, and I know that I can put anything into this and always get a value back. So my domain is negative infinity to positive infinity. And this is my actual function value x. In example 7, let f of x equals square root x, g of x equals x minus 3, and h of x equals 2x. Write each given function as a composition of appropriate functions chosen from f, g, and h. Part A, we have capital F of x, so capital F is a different function from the lowercase f. Capital F of x equals square root of x minus 3. So we've got to figure out which of these functions up here were used to create this new function, and how can we write it as a composition. Okay, if you look carefully, just look at f and g functions up here. You can see that the x minus 3 was substituted inside the square root. In other words, the g function was put inside the f function. So to create this capital F of x was created from putting the g function inside the f function. So that means you were doing f composite g. Let's check that to make sure that we're correct. So to check f composite g, I put my g function inside my f function. So that would give me the square root of x minus 3. And that's exactly what the original function was. So that's the correct answer. And this is the answer. For part B, we have capital H of x equals 2 times the square root of x minus 3. There's a little bit more going on this time. We've got, so I'm going to let you look at it for a moment and think about it before I tell you exactly what has happened. If we just look at the 2 times the square root of x by itself, okay, so just kind of ignore the minus 3 for a second. Looking at this can be created by substituting the square root of x into the h function where the x is. So this piece alone would be f inside h. So if you put f inside h, that would be h composite f. And then from there, now if we put this 2 square root x inside the g function, that gives us the 2 square root x minus 3. So what's happened is we are doing f needs to go inside h, and then that result needs to go inside g. So we want to do g composite h composite f to get the capital H of x function. Let's check our work and see if that's correct. So if I calculate this, I need to do f of x inside h. So put f inside h. I've got 2 times the square root of x. So that was h composite f. And now I need to put h composite f inside g. So that gives me g composite h composite f equals, put this inside g, and I've got 2 square root x minus 3. So my answer was g composite h composite f. And it checked out because it gave us what we started with here. Okay, and that completes section 2.4, operations with functions. So we will go over this material again in class. So just make sure that you remember to complete your quiz in time for class, and make sure that you complete all of your guided notes. Go back and listen to any portions of this that you're not clear on, and we will discuss it in class.